Okay, we're doing page 8 of binomial expansion addendum, and we're going to start out with a pretty bizarre problem, 13b, where we have 1 plus x to the power of n, and they said to use that to deduce the following expression below, and this is also a pretty bizarre expression. You might say, okay, what the heck do I do? But if you look at all the combinations that are expressed here, you can see that there's a pattern where the top number is 2n plus 1, right? So if you want the top number to be 2n plus 1, basically that means that the degree of the binomial expansion has to be 2n plus 1. Okay, so although it says to use 1 plus x to the n, what you're going to start with is 1 plus x to the 2n plus 1, because that is the top number for all these binomial expansion coefficients. So you need to start there, okay? And even though this is not every single coefficient, don't worry about that yet, okay? All right, so if you have this and you're going to expand it, what you're going to see is something that kind of looks familiar with what we have above. You would have this coefficient. You would have 2n plus 1 over 1 coefficient. You would have 2n plus 1 chooses 2 coefficient, etc. Right? So you'd have all these coefficients, and it would go all the way up to 2 to the n plus 1 chooses 2 to the n plus 1. That would be the last coefficient, right? And each one of these would be multiplied times an x term. So this would be x to the first. This would be x squared. This would be x to the 2n plus 1, right? And when we look at the fact that the base of this exponent here is 4, you might think that, oh, okay, so 1 plus x, I should try to make that equal to 4, and you're thinking, okay, x equals 3. But actually, if you look at it, if you put 3 in for x, you would end up with 4 to the 2n plus 1. And 4 to the 2n plus 1 is actually much bigger than 4 to the n, right? So let's do a little trick here. Actually, the x value, if you put x equals 1 in here, then the left side is going to become 1 plus 1, or 2, to the 2n plus 1. Now we'll take a page out of the exponential chapter, and if we look at 2 to the 2n plus 1 and we break that down, that's equal to 2 to the 2n times 2 to the 1. And so 2 to the 2n is actually could be grouped as 2 squared to the n times 2. So that's actually equal to the 4 to the n times 2. 4 to the n, that's exactly what we wanted, right? So I think that we have something here. We should indeed make x equal to 1. So if we make x equal to 1, the left side is going to be 2 times 4 to the n. The right side is going to be, all these x's are just going to disappear because x is equal to 1, right? So then I just end up with all these Pascal's triangle coefficients added together. Okay? 2 to the n plus 1 chooses 2, and so on, all the way up to 2 to the n plus 1 divided by 2, or chooses 2 to the n plus 1. Okay? How many coefficients do we have here? We have 2 to the n plus 1, 2 to the n plus 2 coefficients, right? Because this is the 2 to the n plus 2th coefficient, right? Because the first coefficient has chooses 0. Remember something about Pascal's triangle coefficients? Pascal's triangle coefficients are symmetric, right? So the first half of the coefficients are mirror images of the last half of the coefficients. And do you see how this is multiplied by 2 here? If this is multiplied by 2, basically we could say is, well, what if instead of multiplying the left side by 2, if we just say, okay, instead of instead of having the whole set of Pascal's triangle coefficients, what if we just took half of the Pascal's triangle coefficients? So we're going to divide the left side by half, and on the right side, instead of dividing by half, what we're going to do is we're just going to eliminate the last half of the Pascal's triangle coefficients, and we're going to keep the first half. So the first half of the Pascal's triangle coefficients would be 2n plus 1 chooses 0, 2n plus 1 chooses 1, etc., all the way to the n plus 1th term, which would be 2n plus 1 chooses n. Does that make sense? Because the n plus 1th term would be choosing n. Okay? And that would be the last coefficient, because the other coefficients, the other n plus 1 coefficients, are just reflections of the first n plus 1 coefficient. So we just eliminate them, and we also eliminated the 2 there. Okay. I hope that's not too hard to understand. I'll explain it in class better if you still have questions. So now we have 4 to the n equals this expression here, which is a bunch of the half coefficients. And wait a second, that's exactly what we wanted. Okay? All right. Let's go to number 15. Consider the expression x squared minus 3x plus 1 trinomial squared equals x to the 4th minus 6x cubed plus 11x squared minus 6x plus 1. The sum of the coefficients in the expansion is 1 minus 6 plus 11 minus 6 plus 1. And if you add all those together, you are going to get 1, right? 1 minus 6 is 5, negative 5 plus 11 is 6, 6 minus 6 is 0, plus 1 is 1. Okay? So, yeah, that's true. Now what are they going to say? Okay, find the sum of the coefficients in the expansion of this big mess. Okay. Did you notice that when you say, okay, let's add up all the coefficients of the right side, that basically what you're doing is you're substituting in x equals 1 in for the x's here, and then that basically turns this into the sum of the coefficients, because if x equals 1, the x's part of it just kind of disappears, and what's left are the coefficients, okay? So if you put in x equals 1 on the right side, basically all these numbers just add up the coefficients. If you put x equals 1 on the left side, you're going to have 1 minus 3 plus 1, which is negative 1. Negative 1 squared is just 1. So basically the coefficients on the right side added up give you 1 on the left. Okay? So, and the reason why I could think of that is because in all these previous problems we've been doing, we've been doing fancy things by substituting in basically x equals 1. Substitute in x equals 1, some weird things start to happen. Some interesting things start to happen. So let's try that with here. So find the sum of the coefficients in the expansion of blah, blah, blah to the 100th. Obviously, we are not going to do the binomial expansion of this on the IB exam. We only have like 6 minutes to do this problem. We are not going to expand it into 101 terms, right? But we do know from doing this that we can easily find the sum of all the coefficients of a binomial expansion if we make x equal to 1. So if we make x equal to 1 on the left side, that would give us the sum of the coefficients, right? So let's just plug in x equals 1 on the left side. Like, pretend that the right side has a 101 term expansion of this, and we are summing up the coefficients. How do we sum up the coefficients? We substitute in x equals 1. If we substitute x equals 1, the right side becomes the sum of all the coefficients, and the left side becomes a pretty easy expression, 1 cubed plus 2 1 squared plus 3 times 1 minus 7 to the 100th power. 1 cubed is 1, 2 times 1 squared is 2, plus 3 minus 7. That basically is 6 minus 7, which is negative 1. Negative 1 to the 100th power is equal to positive 1, right? So that's it. the sum of the coefficients in the expansion is positive 1. All right. Last problem with 2 parts, 17a. Write down the first 4 and the last 2 terms of the binomial expansion 3 plus x to the power of n. Okay, so here I've done the expansion. How did I do the expansion? Basically, first I just put in the Pascal triangle coefficients using the expressions for n chooses 0, n chooses 1, n chooses 2, n chooses 3. N chooses n minus 1 is the second to last term's coefficient, and n chooses n is the last term's coefficient. Now, we can simplify this a little bit because n chooses 0 is 1, n chooses n is 1, so we could eliminate those, right? Now, look at the a value. The a value for the binomial is 3. So the a value I put here is 3 to the nth power, 3 to the n minus 1's power, 3 to the n minus 2, 3 to the n minus 3, and so on. The last term, the second to last term is just going to have 3 to the first power, and the last term is going to have 3 to the 0th power, so the last term doesn't need to have the a written down at all. Last of all, the b term is x, so the first term has x to the 0, the second term has x to the first, the third term has x squared, the fourth term has x cubed, and then the second to last term has x to the n minus 1, and the last term has x to the n, right? Now we can simplify it a little bit. We can eliminate the first and last coefficient. They're just equal to 1. So basically we have 3 to the n plus, and the second term, actually, this coefficient here is just equal to n, right? But let's go ahead and leave it because we have it down here in part B. We'll look at that later. 3 to the n minus 1 x plus n chooses 2, 3 to the n minus 2x squared plus n chooses 3, 3 to the n minus 3 x cubed, and so on, right? Now it says, hence find its simplest term, the sum of this series here. Look at this series. This series looks almost exactly like the series we just drew. So for example, 3 to the n is 3 to the n minus 1, 3 to the n minus 1, x. Oh, but look, this ours has an x squared, x cubed. Theirs doesn't. How would we get rid of x squared, and x cubed? Well, we're going to do what we did in the last few problems, which is we substitute in x equals 0. If we substitute in x equals 0, then this expression that we have here magically turns into this expression, right? Basically, the expression that we have above is the same expression except we have x's in it. The x's disappear when we make x equal to 1. Then it says, find the sum of this series. Okay, this is a series, basically. It's a bunch of, a pattern of numbers added together. How do we figure out the sum of this? Well, we know that the top expression is equal to this binomial to the nth power. So this expression must also be equal to 3 plus x to the nth power, except we know that x equals 1 in this case. So we could say it's actually equal to 3 plus 1 to the nth power. 3 plus 1 to the nth power is 4 to the nth power. So basically what we know already is that part B of 17 is actually equal to 4 to the nth. And that's it.